Welcome to a series of classes on mathematics of machine learning. We are dealing with definitions in vector space. The first definition is the definition of linear combination. Let's suppose that you have a bunch of vectors x1, x2 till xn. Let them be part of vector space V. Let's also suppose that we have a bunch of scalars alpha I which belong to R. The multiplicative addition of these vectors along with these scalars alpha 1 x1, alpha 2 x2, all of them belonging to vector space V, is called the linear combination of these vectors. So you have a bunch of vectors which are part of vector space. If you multiply each one of these individual vectors with a scalar and add them together, and if that resultant vector is part of the vector space V, then we say the resultant vector is a linear combination of these vectors. Another interesting fact about standard vectors is that alpha 1 e1, e1, e2 here being standard vectors, implies that all the coefficients have to be 0. So if these, taking these facts, taking the fact that the additive resultant of all these vectors, if it belongs to vector space V, and if these vectors happen to be standard vectors, then the sum ought to be 0. It's an interesting way to look at it. Geometrically, it means that no more than 2 vectors lie in a plane. This is very interesting because if they are standard vectors, there are only 2 of them that lie, 0, 1, 0, 0, 1. So the third one kind of protrudes out of the plane. So this is not part of the plane. As a result, on a 2-dimensional plane, only 2 vectors lie on it as long as they are standard vectors. Now this can be generalized as follows. We can say that vectors x1, x2, xn, let them belong to vector space V over R. Let them be linearly independent if for alpha I that belongs to number line I takes the value from 1 to n adds up to 0. So the scalar product of individual vectors, and when you add all these vectors, if they result in 0, that is the definition of linear independence. Basically, that would mean x1, x2, xn are linearly independent. That would also imply, by definition, that when this is only true if alpha I is 0, where I takes the value from 1 to n. Standard vectors have another interesting property, that any vector in Rn can be written as a linear combination of it. So that means you take any vector, let's say that vector is x in an n-dimensional space. This vector can be represented as a linear combination of standard vectors. So this is e1, this is e2, this is en. Okay, another definition that we should be aware of is the definition of a spanning set. So we'll deal with it here. We say that vectors x1, x2, xn in a vector space V over R spans the vector space V if for all x that belongs to V, there exists alpha I that is part of number line where I takes the value from 1 to n, such that they form a linear combination. So the idea here is, if you have a bunch of vectors which kind of whose linear combination forms a vector which is part of vector space, and this is not quite clear with the definition here. Let's say any vector. So for example, if you have 3 standard vectors, E1, E1, E2, E3, and the linear combination of these ought to be 0, then these three standard vectors spans space R3. True? Yes. Sure that linear combination of these will add to 0. But if this were not to be the fact that these are not standard vectors, then they form something called a spanning set. So I think this exercise kind of proves it. Like if, let's say, if x1, x2, xn spans the vector space, basically what it means is, if you have a point in that vector space, you can get to that vector space with this set. So if you have a spanning set, you can reach any point in that space. So R3 is the space, and if you have these standard vectors as part of the spanning set, you can reach any point in R3, is what it's trying to say. And let's say if these vectors are redundant, let's say there are 4 vectors which form the spanning set of R3, they too span the entire set. So there are redundancies in spanning set. There can be 2 spanning set of vectors which span the vector space. And you can remove, let's say if there are 4 vectors which form a spanning set which spans the vector space, you can remove one of the vectors, and you can keep removing one vector at a time until it loses the spanning property. So if you have 4 vectors and they span the vector space R3, let's say they're all linearly independent, then if you remove 2, then it loses the property, like as it is stated here. If you remove 1, it's perfect. It spans the vector space with minimum number of vectors. The minimum number of vectors required to span the vector space is usually sort of the dimension. So we'll see this in the next definition that we have in terms of dimension. So let's say the set x1, x2, xn, that set is called basis vector of vector space V. If the set is linearly independent and spans the vector space V. So these need not be synonymous. I mean, they are mutually exclusive. The set ought to be linearly independent, and then they ought to span the vector space V. If that is true, then this n here represents the dimension of the vector space. So it's quite natural to ask, since a spanning set there were redundancies in spanning set, that would mean spanning sets were not unique. Our dimension is dimension unique. So by definition, is dimension unique would obviously have the answer in the affirmative. This requires us to prove a lemma, which we call the replacement lemma. Okay, what does the replacement lemma basically say? I mean, the statement is important. Okay, lemmas are used to prove theorems. So lemmas do a lot of operation inside a theorem. So these are like the building blocks of a theorem, let's say. So we have a lemma which is called the replacement lemma, and by definition of this being a lemma, I will use this lemma to prove something else, which will be called a theorem. So this replacement lemma states, the statement is, let v1 till vn be a set of basis vectors in V, and let V non-denominational, non-subscript V be any non-zero vector in V. So these form the set of basis vectors in V, and V be any non-zero vector in V. Then there exists a vector Vi such that V1, V2, Vn included forms a basis. Okay, Now what are we trying to do? We are saying that there is a set here which forms the basis, the minimum number of vectors which span the vector space, which is the basis. And let's suppose that we replace one of the vectors with v. This also, which is part of vector space v, that also forms the basis. Let's prove this. Okay, so let's say we have v which belongs to vector space v. V is a vector that belongs to vector space v. We have v1, v2, vn which forms the basis vector. So essentially what you can say is this v is equal to alpha 1 v1 we can write this. This is like the preliminary step for this. Implies this. So what we're trying to say is, which is when you're trying to solve for this vector v1, right? Assume that we have an expression for v1 which is basically linear combination of vector v and a bunch of vectors taking the index from 2 to n, which are indexed by j. So this is a linear combination of vectors, linear combination of v, v2 and vn. As you can see, v1 is not included. We have replaced that with v. Then it easily follows that this set of vectors span the vector space v, right? By definition, we have replaced it with another vector which is part of the vector space v. This still spans the vector space v. True. Now we will write this statement, let's call it equation 1, and 1 with some substitutions for 2. You introduce new terms bk and beta 1. Okay, and we also define here that this implies that beta I is 0. Why is that? Let's see. Why is this 0? For this to be 0, this ought to be 0. And why is that? So when you substitute vector v with a combination of alpha I, vi, we get beta 2 v2, beta 3 v3 till beta n vn, and then add beta 1. Essentially expanding this is here, beta 2 to beta n vn, which is here, and this we just substituted this value, right? Substituted this value from our definition. Here. So this portion is from, let's call it 1a. Okay, this substitution is from 1a. So when you fill that in, when we segregate based on vector v1, vector v2, vector v3, you get a nice form in terms of beta 2 plus alpha 2 v, beta 1, like this, beta n plus alpha n beta 1. there are numerous terms in between. So to proving that beta I is 0, that also means that by linear independence of v1, v2, v3, when linear independence means what? So the linear combination is equal to 0. That would mean all these terms are 0, and all these terms are 0. So the first term is 0. If the first term is 0, we know alpha 1 has value. That implies beta 1 is 0, because alpha 1 has some value. This ought to be 0. If beta 1 is 0, then this whole term becomes 0 and beta 2 is 0. Likewise, you prove that beta 1 is 0 because alpha 1 cannot be 0. So this is true. We know this is true. And we know alpha 1 cannot be 0 because at the beginning of the proof, we assume that alpha 1 is not equal to 0. So we at least need one term, in this case alpha 1, to be not 0. So if alpha 1 is not 0, beta 1 is equal to 0. If beta 1 is equal to 0, this term becomes 0, this term becomes 0, as a result of which this is a linear combination. So then all the coefficients have to be 0. Therefore, the new replaced vector spanning set is still linearly independent. So you took a vector set which was the basis of vector space V. We replaced one of the vectors which was part of the vector space, and it still is linearly independent. So this lemma forms the basis for the theorem that the dimension of the vector space is unique, which is what we wanted in the first place. That's the theorem. Dimension of the vector space is unique. So the way you prove it is this is a proof by contradiction. Suppose, say that dimension is not unique, and let's say there are two sets of vectors v1, v2, vn, un, u2 till um, and let's say m and n are not equal, and without loss of generality, m is less than n. It's a very important point. I mean, this forms the basis as to for why this is true. So you have two sets of vectors, v1 to vn and u1 to um. Indices are different, m and n. M is not equal to n. M is also less than n. For this to work, let's say we take one of the vectors. These can be zero vectors too. So let's say we take one vector from the smaller vector set u1, and let's suppose that is not equal to 0, okay, which is very important. Let's take u1 and replace it in this set. Okay, we assume that both these are linearly independent. That is something that needs to be stated, but isn't here. But let's suppose that is true. So if we replace v1, if we replace u1 in this set v1 to vn, this results in this set u1, v2 until vn, which is linearly independent. You just replaced one with the help of previous lemma, where you've seen if you replace one vector, which already forms the basis and is linearly independent, the resultant vector is also linearly independent. So you took one vector out and you replaced it with one. So u1, v2, this is because of replacement lemma, not reinforcement learning, for sure. Replacement lemma. It's an acronym which is never used. I think very few people who practice machine learning have encountered this acronym before. But anyway, I hope in the shortage of time people can recognize this acronym to be RL. Now, if you continuing with the proof, now you replace the same thing with the second vector. You replace u2 with v2. Now u1, u2 also is linearly independent. You keep replacing each one of these vectors of the shorter vector set to vn. Okay, you keep replacing every one of these. Since m is less than n, you can plug the entire vector set into this and still will be left out with some of the vectors, as you can see, as can be seen here. At each step of replacement, you still know that each one of these vector set is linearly independent. Now we already know by definition that u1 till um is linearly independent, and now we've replaced u1 to um in vn to vm, which is much less because m is less than n. So we have additional vectors. We also know that v1 to vn used to be linearly independent. Now we have a contradiction of sort because we already proved this is linearly independent. You cannot, if there is a linearly independent set, you add one more vector to it, the resultant set is not linearly independent. There will be redundancies, which is a contradiction. So m ought to be equal to n. There's no way this statement would hold unless m is equal to n, which proves that vector space has unique dimension. We proved that. Another exercise is prove that any set of vectors having more than n elements are linearly dependent. Yeah, they'll still span the set, they just won't be linearly independent. Okay, let's use this for basis completion lemma. Nice acronyms, these BCL. The theorem states something like, it's not a theorem, lemma 2 states any linearly independent set of vectors in an n-dimensional vector space can be extended to form a basis. Okay, any linearly independent set of vectors in an n-dimensional vector space can be extended to form a basis. Okay, how do we prove this? We have a bunch of vectors, v1 to vm, m is less than n. Let that be independent set of vectors in vector space V. By assuming that the basis exists, okay, basis always exists. Let's assume that the basis exists, and let u1 till un be basis vector. By replacement lemma, third laws of generality, all this, you replace every one of the vectors of u v1 to vm into the set, since n is greater, retaining the basis property. It's same as the previous lemma. This is indeed an extension of the basis vector. The above theorem relied on the fact that basis exists, which seems questionable. However, thanks to the following remarkable theorem which proves the existence of basis. So basically what this sets it, basis completion lemma. So if you have a linearly independent set of vectors of n-dimensional vector space, that can also be extended to form another basis. So this sets up for theorem 2. In any finite dimensional vector space, there exists a basis. So you take any finite dimensional vector space, there exists a basis. Okay, which is proven by Son's lemma. Okay, there's an exercise to prove any vector in finite dimensional vector space. Prove that any vector in finite dimensional vector space can be uniquely represented as a linear combination of basis vectors. Like the linear combination of standard basis vectors. Yep. So in the title, one may wonder what a vector space has got to do with matrices. Okay, this will take it up in another session. Okay, let's finish this off. So basically, what we're trying to say is, what does matrices got to do with vector space? And let's say you have a matrix where elements are indexed with I and j element. Okay, and let's say such a matrix exists in R n cross m space, where this denotes the element of the matrix, which is part of a number line. It's a scalar element. Denote the set of all matrices of dimension m cross n. It is easy exercise to show that it is a vector space over R of dimension mn. Okay, this matrix exists in a vector space mn, m into n. However, this turns out to be not so elegant way of looking at matrices as vector space theory. How do we will represent a way of viewing matrices as a representation of linear map for a given basis. Okay, that's it. That concludes the definitions pertaining to vector space, which will be useful. So in this session, we covered replacement lemma, based completion lemma. We also proved that dimension is unique. We got an idea that every finite dimensional vector space there exists a basis. That's pretty much it. Let's catch up next time. Take care.